All right, my name is Jeff Heacock again. We're going to start lab number 6. There's some things that we're going to talk about today, but what we'll do is we're going to start out talking about different fasteners. Last week we talked about threads and whatnot, and now we're going to actually look at fasteners, all right? Fasteners are a very important thing. If you're designing something as an engineer, how you attach two pieces together is going to be critical, right? Very rarely are you going to engineer something that's just a standalone part that is what it is, right? Usually things have to come together to make an assembly, right? But you can't assemble things without fasteners, all right? So there's mechanical fasteners such as screws and bolts and things of that nature. What other kind of fasteners are there? Well, there's like chemical fasteners like glues and epoxies and such. You also have like rivets and stuff like that. You have welding is actually considered a fastener, right? That's a way to get two parts together. So there's many different things, but what we're going to do down here is we're just going to focus on standard bolts and fasteners like that. So we're going to zoom down here, and I've got some examples, all right? So it's imperative that you know what is available, right? The more you understand what is available to you, the better you can design things. I've had many students that fasteners were an afterthought and to their project, and when they got it all bolted together, nothing fit together because they did not include enough room for the bolts, all right? So right here I've got 3 different kinds of bolts that you may have seen before, all right? This first one right here is called a cap screw, a socket head cap screw, all right? It's got the thread down here at the bottom, and it's got a square shoulder on it, and at the top it drives with an Allen wrench or a hex head, all right? So that's what a socket head cap screw looks like, all right? This is probably the most common fastener you'll see in a lot of industry stuff, all right? This next thing is called a flathead cap screw, all right? You can see it's got the thread here. It's also angled here. It's got a flat top, and it uses an Allen wrench as well to drive it, screw it in and screw it out, all right? So those are the 2 most common that you'll see around a machine shop, all right? Here is an example of a carriage bolt, all right? Or a hex head bolt. All right, you've got some thread down here. This thing doesn't need to be threaded. This usually has a nut on the back side. Everyone's probably seen this. But it requires, the difference between this and this, all right, is that it uses a wrench or a socket to drive this hex head. All right, so it's important to know which kind of fasteners you're going to use to put your assembly together, all right? If you design something, you've got to make enough room for the head of each one of these if it's important to you. All right, so we'll come back here to the board, and what we'll learn today, the first thing we'll talk about is a counterbore, all right? And all a counterbore is it's just a pocket for a bolt to sit down in. So we use this socket head cap screw, and we would cut a little pocket in here with a through hole for this bolt to sit down in here. Obviously it's not to scale, but you get an idea that this counterbore will be placed in here so that the head of the bolt is underneath the surface of your part, all right? So the thing would lay something like that, all right? With this being the threaded end. All right? So, the head of this bolt is underneath the surface. There's a lot of times where you don't want, if you had just made a hole, this head would sit on the top of this, and a lot of times that causes interference in your assembly, so you have to recess it down into the material in order to hide that cap screw. All right? So, let me kind of try to erase this a little bit, because there's just a couple key features that we need to know about this counterbore. All right? All right, I think we're close enough to getting there. All right. So, if you turn to part number 3, all right? Part number 3 or item 3, it should be called the spring cup. All right? There's a call out there. If you look at the front view here, all right, in that example, it says diameter 0.20 through all. Then it's got this symbol. It says diameter 0.31. And it's got this symbol 0.06. So this is a call out for a counterbore. Okay? How this is read is this first number right here is going to be the diameter of the through hole. All right? So we need to know this diameter. It always depends on the type of the size bolt you're using, but you need to know this diameter. So that's going to be your clearance hole. You always want that over whatever, larger than the major diameter of the bolt going through it. Obviously, if I'm trying to put a 1/4 inch bolt down through here and my through hole is only 0.2, the bolt's not going through, right? So you need to know the clearance hole size. Here, you also need to know this diameter. All right? That diameter, which is actually the size of its clearance for the head of the bolt. All right? The last thing we need to know is this. I'll just make that a D for the depth. All right? Those are the 3 components that you're going to need to know when designing this. All right? So, in our example, this right here is going to be our through hole. So, it's going to be 0.20 inches. All right? Through all just means it's going to go through the entire piece. All right? That's pretty self-explanatory. All right? This symbol right here is a counterbore symbol. All right? That's just the symbol on a drawing that says this is a counterbore. All right? This diameter is going to be the diameter of the head of our bolt. All right? So, for our example here, that would be diameter of 0.31. All right? This symbol right here, this down arrow, is just a depth symbol. All right? And then this is the value of that depth. So, right here would be 0.06 for this example. All right? So this is how the nomenclature, or how it's shown on a print right here. All right, so it's very important that you understand how that is all put together. I see a lot of people's drawings that just have, that call it out the hole, and then they dimension the hole, this counterbore hole, and then the depth, and they use 2 or 3 different views to express one feature. Because me as a machinist, look at this as just one feature, all right? And then the feature can be explained just with this right here. It doesn't need 2 or 3 different views to tell me all the different depths. All right? If we look at if you look at your drawing at number 3, right, it only has 2 views. All right? But the actual counterbore in that is only shown in just one view. All right? So this is a counterbore. All right? The next thing we want to talk about is the countersink. All right? The countersink achieves the same thing as a counterbore in that it hides the head of the bolt below the top surface of the part. But instead of putting a cap screw in there, we put in the flathead cap screw. All right? Which makes sense because it's got an angled bottom. A lot of times you'll see these being used in thinner materials, right? Because if we look at the 2 different heads, all right, this one is not as deep, all right? It actually contacts more surface area. So it's more ideal for thinner parts, all right? So a countersink sits down in here and it will hide the head of this bolt down in here, all right? There's an example of this on part number 9. All right, let me turn to part number 9 myself. All right, so part number 9 is something we're not going to deal with until we get in the mills, so it's later on down the road. But it's an example of a countersink. All right. So there's only 3 main components for a countersink. All right. The first is this angle. We need to know the angle. All right. We need to know this diameter. And we need to know the maximum diameter at the top of the surface. All right. So if you've turned to part number 9, our example there looks like this. We'll say diameter 0.20 through all. It's got this symbol, diameter 0.39 by 82 degrees. All right. So much in the same way that the counterbore is laid out or formatted, so is the countersink. So this is going to be our diameter here for our through hole. So that's going to equal 0.20 for this example. All right. Through all just means again that it's going to go all the way through the part. This symbol right here is the countersink symbol. That just denotes that, again, we are creating a feature that's a countersink. All right? This diameter is the maximum diameter, or the diameter across at the very top. So .39 would be this, right there. All right? The problem with countersinks is there's no real great way of measuring that, all right? You can't get calipers right here at the edge of these corners. All you can do is really approximate. So a lot of times what we'll have to do is make a countersink, and we'll actually have to test fit it with our bolt. And if we haven't gone down deep enough, our bolt will still stay above the surface. And then we just have to keep working it down until it is comfortably below the surface. All right. So this is a very hard number to measure. All right. So typically, whenever I make countersinks, I have the bolt that I'm using on hand, so I can always fit it in there, and I know that I made it correctly, because measuring this is near impossible. All right. Now, this 82 degrees is going to be your angle right here. That's going to be our angle. All right. So when you choose your fasteners, you need to know what this angle is on your bolt. All right. So here's a rule of thumb. If you use standard imperial hardware, so your inches and your half inches and stuff like that, so your SAE stuff. So those will be at 82 degrees. So all your unified stuff, your SAE, pretty much all your English hardware. All right. Now, metric hardware typically is 90 degrees for metric hardware. So this is a rule of thumb. All right. Rule of thumb. They do put 82 degrees on metric and 90 on English hardware, so you still have to really know, but this is just a general rule of thumb. All right. So these are the two call-outs. All right. So you're probably wondering, well, where do I go to get this kind of information? Well, what you can do is you can go to the Machinist Handbook, and the Machinist Handbook has just got a great big table. I'm not sure which page it's on. I guess it depends on your edition. It will have a table, and it will say all 1/4 inch hardware. It will need to have a diameter this big, a through hole that's this big, and a depth that's this big, and we'll give you the values so you can use. If you don't have the Machinist Handbook, it's a very useful resource. I mean, it's got hundreds and hundreds of years worth of knowledge, all collated into one nice book. All right, it's a big book, and it's sometimes hard to navigate. But if you're trying to design something, knowing these values are important. I said earlier that I had a student that didn't account for all the counterbores. And this person was using really, really thin stuff, like sheet metal stuff. And then they were going to plan on using cap screws. So they had all these cap screws, but all the cap screws, you couldn't counterbore it deep enough to hide the top of that bolt. So their parts didn't come out the way as they wanted it or designed. I don't think it actually ended up working for them because they did not take into account that the head of the bolt has got, it's got some size to it depending on the size hardware. If you want it off of this surface, you're going to have a part that's thick enough to hide that. All right. So the Machinist Handbook will give you the values for specific hardware, because I said in the last lecture that all hardware has been pretty much standardized. All right, so they all have to fit into the appropriate box. That way, they're all similar. It doesn't matter if you buy it from China, from Ireland, or from USA, wherever it's made, it's got to follow the rules of being a bolt in order for it to be sold. All right? So there are times where you as an engineer can design different, you can change the values of here based on your part. All right? For example, let me erase this right here. All right? All right. So, let's say we want to make a counterbore for this. This was our hex head bolt. All right. Now, what if I just go ahead and I measure how big this bolt is right across here? And I said, I want that to be that value. What's going to be the problem with that? The problem is, what does it take to turn this thing? It takes a socket, right? Or a wrench. Or some other, a tool to come down and actually rotate this, right? These other ones, we access it from the top of the bolt, all right, to drive it. But this one, we have to access the sides, all right? So, in a case like this, we'd have to change the diameter of this top one much larger, something like this. So now when our bolt goes down in there, we've got room to put a socket or a tool or a wrench or whatever needs to happen on that bolt. All right? Because I tell you, if you just make a counterbore that just barely fits this, you'll have no way of driving that bolt in or out. All right? So that's if we wanted to manipulate our counterbore depth. All right? This will always pretty much stay the same, right? Because the size of this is always going to be, depending on, doesn't matter which head here is on here, this through hole is going to always be just enough to get this bolt down through. All right, so that's if we want to manipulate the counterbore. There's also times where we want to do the depth as well. All right, I'm sure at some point everyone's tried to take apart some sort of plastic toy or something from their childhood where the counterbore is really deep down in there. I'm not sure if you've ever tried to do that, take something apart, and then you have to have a really long screwdriver to get down in there. All right? The reason they do it for when they're making plastic parts is for two reasons. All right? Instead of having, if they just put in a counterbore up here, they'd have to have a really long screw that come down here and attach whatever's down here, right? The bolt would have to be this long. All right? Which is, you know, might be an extra penny. But when you're making millions and millions of these things, those pennies start to add up, right? So what they'll do is get something. Now they just need that little bolt that's this long, all right? And so that engineer just saved the company tens of millions of dollars by saving, you know, 5 cents a part, times millions of parts, times however many bolts or fasteners are in here, right? They also save money because all of this that would have otherwise been plastic is not plastic anymore. So they save money and material costs, all right? Yes, it may be a pain to get a screwdriver that's this long down into something, but it's easier to make one really long screwdriver and save millions and millions of dollars in doing it. All right. So there are times where you can manipulate this depth. All right. So it's all dependent on your design. Typically, shorter bolts are a little bit stronger and more rigid, so having that depth, if you've got a really large part and having a large counterbore, and then, which means you only need a shorter bolt, could make your assembly a little bit better. All right. As for countersinks, there's really not much you can manipulate. I mean, you could always drive this down further, but you get to a point where it doesn't really benefit you anymore. All right. The one other thing that's kind of a combination is it's kind of like a counterbore, which we'll do on another part later. It's called a spot face or a spot face. All right. I'll write that down here. All right, spot face. What that is usually just a really thin, a really shallow counterbore. So you see them a lot in castings. So if you've ever taken parts out of your car, you know the surface of a casting is pretty rough. All right, and if you have a hole that needs to go through it, and you want to put a bolt. You want to put a bolt in here. It's only going to contact on these high spots and not contact over here, which is not good. All right, it's going to make that bolt fail much quicker, right? Because it's not distributing its load. So what a spot face will do is take this irregular surface, all right, and we'll just cut it back just a little bit like this. All right? Just a little tiny thing like that. So now, my bolt has something flat to sit on down here. All right? It's hard to draw that in there just right, but it's pretty much just a little machine flat. Usually I'm not with a spot face. I don't care if the head of the bolt sticks past the surface, but I'm more worried about this right here where it contacts the bolt and give it a better place to see. So that's a spot face. So again, it's like a counterbore, but it's just a really shallow, just to give the bolt something flat to sit against. All right, before we get into anything else, I want to show you a couple of ways, or the way that we're going to be able to put our counterbore in to our parts. All right, so if we go back to item number 3, is what we're going to be making. Here's the drawing here. Hopefully you can see it. Here's our call out. All right, so we need to find a way to manufacture that. All right, the way we manufacture here is by using these things. These are called end mills. All right, they're typically designed or typically used on a mill. All right, which we haven't gotten to, but there are a handful of applications on a lathe, and counterbore is pretty much the main purpose of using them in a lathe. All right, so this is what they look like. All right, I got 2 different styles here. One has got these ridges here, which makes it cut differently, but I don't want you to be concerned about that. All right, right here, all of these right here are the cutting flutes. All right, so this one right here has got ridges on it. Again, it has nothing to do with how you use it on the lathe. All right, what there is a difference is we have to look at the very ends. All right, when using them in the lathe. All right, Because what we're going to end up doing is just plunging this in, all right? If we look at this 3D model here, we're going to end up just plunging this right into and creating this counterbore. Or I guess if you think of it like that, we're going to plunge it right into the material, all right? So there's two kinds of end mills in the world, all right? There's center cutting and non-center cutting. If we look at this one, we've got 4 flutes here. Each one of these is a cutting edge, all right? So we got 4 flutes, all right? If we look right here at the very center, you can see that all the flutes come together at the very center, all right? I don't have a little pointer to point to it, but they're all ground together, all right? They come together. So this is a center cutting. So this tool is designed to cut right at the center. It doesn't cut very well at the center. It's not great for the tool, but it can do it, all right? So we can use that to plunge into material, all right? This is an example of a non-center cutting. As you can see, there's a pretty visible hole or a recess right at the center where all those flutes would have been ground to. All right? This is an example of a non-center cutting. So this, if I plunge this straight into a piece of material, what would happen is all that material would load up this hole and load up all these flutes, and wouldn't actually they won't be able to be cut. They're just going to get smeared and packed down in there. So we don't ever want to plunge this non-center cutting tool into a material, all right? That's bad for the tool and bad for your part, all right? So make sure when you are making counterbores that you choose the correct end mill, all right? All right, so continuing with Lab 6, we just did counterbores and countersinks. The last thing we're going to learn on the lathe, this will actually be the last time this is the last lab where we'll actually use the lathe. So we're just going to get to the final thing that we got to learn about. All right, before we get started here, if you remember with Brian, we've made this little crank face, all right, a little crank, which was part number 8. You also made these pins. This one just happens to be number 11, all right? So these have to come together and make one piece, but we can't just push this pin in the hole because it's slightly smaller. We've got to actually press these two together. We'll use an Arbor Press to achieve that, because no matter how much I push on this, I'll never be able to get these together. So we have to use some mechanical advantage, and we'll use a press, which I'll show you here in a little bit. But these are the two pieces that we're dealing with. Imagine that for a moment that they're put together and assembled. All right? So what I've drawn up here is part number 11 and part number 8. All right? Being pressed together, and now 2 become 1. All right? The reason we're putting them together as well, they go together, and what we want to achieve on this is truing up the crank face. Okay, when we push these two parts together, they might not be exactly perpendicular. All right, it could be a little bit off. So when it rotates, the crank face will do some sort of it will run all kind of crooked. All right. We don't want that. We want it to spin nice and true. That way, the action of our air engine going up and down is a nice, smooth motion. All right. So to achieve that, we've got to balance these out. So once we press these two together, these parts by themselves are too small to hold into a chuck at this point. So we're going to join them together and then have this little sub-assembly that will true up. All right, so Here's our crank face, part number 8, and the crank shaft, number 11. All right? We will hold on to these in a chuck, like so. We're just going to grab the very end of the shaft. All right? And as you can see, I've drawn this crank face on. I exaggerated it being out of balance at this point, right? It obviously is leaning this way. So we're going to try to true all this up. Remember with Brian, he actually had you part this off at 150. All right? 150 thousandths. That's because now we're coming back, we're going to true this thing up and get it down to the right size that's called out in part number 8. Alright? So, right here I've listed all of the steps that we're going to need to do, so I'll kind of walk you through this. I always like to talk people through this, so once you see it at the machine, if you can't see it on camera very well, or even if you were in person, sometimes we're talking little tiny parts, it's difficult to see what actually is going on. So I like to talk through it on the whiteboard. Alright, so right now our crank face is been assembled, but it's out of balance. Alright, so if we were to turn on this thing's going to flop all over the place. Alright? That's not what we want. So, step number 1 is to actually assemble this. Again, I'll demonstrate that out in the shop here in just a moment. The next thing we're going to want to do is a little machinist trick, okay? Because we're taking very light cuts here, and all we're doing is just trying to kiss off some of these surfaces, alright? This step number 2 says, put Sharpie on all the faces of this crank. Alright? What we're going to do is right now, obviously it's steel colored, so it's kind of a shiny gray. But what we'll do is we'll take a black Sharpie and color all around part number 8. Alright? I'm going to do it in green just so you can hopefully see what I'm doing. Alright? So So I'm going to color all of those faces, and it's going to turn this gray thing into black or blue or whatever color Sharpie you have. Preferably black. It actually provides more contrast, all right? This way, when we're at the machine, we can see if we've cut it all the way parallel. If there's a spot on there that still has Sharpie on it, that means you haven't got all the way you haven't cut that face all the way true yet. Alright? So first put on your Sharpie. And then, so step number 3, we'll be facing this off lightly. Alright? All we're going to do is just face enough till the Sharpie is gone. Alright? We're not finding a dimension yet. We just need to find and make it true before we can take it to its final size. Alright? So, it is very, very important that you, through these steps, use very light cuts. Very, very important. And by light cuts, I only mean maybe 3 to 5 thousandths. Alright? Because what's actually holding this part number 8 on to part number 11? The only thing that's holding it on is friction, right? So we don't want to develop so much cutting force that it overcomes our friction force, okay? So that's why we got to take really light, delicate touch. Alright? So, a nice light cut is going to be the name of the game for this part of the lathe. Alright? So number 3 right here just says we're going to face it. Alright? So we're going to come in and then we're just going to run a face. Alright? So if I went from here, I might just knock this off. All right? So now that's getting trued up, but all of this is still going to be colored. All right? So I'm just going to keep, it's going to be different for everybody how many times you have to go. But if I get another cut, it's going to start trimming it up. And the more I take off, hopefully it's only 2 or 3 cuts that you have to make. And eventually, you're going to have this faced off. All the way, so now it's nice and true with this center of rotation, okay? Obviously the center of rotation is right here. I've taken it and I've just kissed off the front of it enough that you'll see no more marker, all right, sharpening. So that's number 3. Number 4 is I want to turn the OD, all right, the outside diameter. All right, so this was a 5/8 in diameter, but we never, at the machine, we never did touch this when we first made this part, okay? So when this comes out of the foundry or the mill that makes it, they just extrude that metal. So it might not be perfectly round, all right? It could have a little egg shape to it, it could have a little high spot, but it's gonna have kind of a rougher kind of surface on it. So what I like to do is I like to just touch that just enough to get some of that material and cut down so it's nice and circular. Because when it gets extruded out and when it cools down, it could shrink to something that's not exactly round. We're looking for exactly round. All right. So turn the OD. So we'll just take our lathe tool, and again, very light cuts. You shouldn't have to take much more than 2 or 3 thousandths off of this diameter. So I'm just going to barely touch it, come off of it, move in maybe 1 thousandths or 2, and just clean this up. All right? Just clean that up. Obviously, it's going to, as it's rotating, will also clean up this side. Right? So now we've got this perpendicular, we've got this parallel with the center of rotation, and it's going to be nice and round. All right? So we've got 2 of the faces that we need. All right? The last face we need to address is this back face. All right? This back face. And back facing is another skill that we're going to learn here. This is the last skill we'll learn here on the lathe, all right? So, with Brian, you've learned that this was a right-handed tool, all right? As it says on the board. But, if I try to go, I can't take this point and make it touch this back part of the crank, okay? So, what we do, you won't have this in your own box, but we'll have community tools, all right? They'll be they'll be slightly smaller, but it's around the same way. The only difference is that it's a mirror image, all right? So instead of the tool sitting in like this, it's going to be mirror imaged over this way, all right? That creates what we call a left-hand tool, all right? We call it a left-hand tool is because we have to take the tool from the left in order to make contact with the material. That's why this was a right-handed tool, right? It comes from the right, and we do all of our lathe work like that. Now, if we have a left-handed tool, it's just going to be a mirror image. That will allow us to take a point and clean up this back face. All right? So that's what we're going to want to do. That is step number 5. We'll take the left-handed tool and clean up that back face. All right? So we just imagine this is over here. When we do the back side, this is a magnet, so it's not going to stick the other way. Doesn't want to erase very well, but we were just taking very, very, very light cuts to clean up just the back, the Sharpie off that back face. Again, we want to take probably even lighter cuts on the back side, because this is going to it's going to want to pop off the shaft more so than it wants to get pressed on. So use really light cuts here. And at this point, after we've done this face, the outside diameter, and the back face, our crank will be nice and balanced. All right? So from there, what we'll want to do is we'll want to measure this dimension right here. All right? We started at somewhere around 150. Probably by the time you're done all of this, it's going to probably be somewhere, I don't know, maybe around 135, we'll just say. But we want to get it down to its final thickness, all right? And if you look at part number 8, the tolerance, or the dimension says 0.123 plus nothing minus 2 thousandths. All right, that's where our final dimension should be. What we want to do is we do not want to back face this to the right width. What we want to do is come back with our right-handed tool and get this and face it down to the right width. So you're going to have to measure and face this to 0.122. 122 thousandths thick. Why do we want to use that thickness? Well, that's because it's right in the middle of our tolerance. Okay, so if I aim for 123 and it was a little bit more, then I'd be out of tolerance. So if I aim for the center of the tolerance zone, it gives me error on either side. A little bit bigger, a little bit smaller, and everything's good. All right, so that's why I aim for 122. Much in the same way an archer aims for the center of the target, right? Nobody aims for the outside of the target. All right? So you aim right for the center. All right? So we're going to try for 122. Obviously, if it ends up 123, we're okay. If it ends up at 121, we'll be fine there as well. All right? Again, light cuts. All right? The last thing we have to do here is there's a small counterbore. It's more like a spot face. All right? More like a spot face. So if you look at part number 8, you'll see right in the center there's a small there's a small circle, right at the center. That was where we reamed. And then there's a circle just outside of that. It says it's a 1/4 inch. All right? What that's going to do is it's going to provide a little bit of relief. Because when we install our piston's going to rub, it's going to be right along this surface. All right? And all we're doing with this little spot face is taking some of this material out of the way. So when we have our piston here, it's not dragging all on this material. All right? Towards the center of the crankcase. All right? So we just want to just relieve it a little bit. It doesn't have to be much. So that's what we're going to start with. Step number 7 on this is going to center drill. All right? We're we're going to center drill it 30 thousandths deep. Remember when we I was talking about the end mills, how they, even though they may be center cutting, they still don't like to cut on center, right at the center, okay? So by using this little center drill, we make a little mark in there, and that gets the material out of the way. That way the end mill doesn't have to worry about cutting the center. All right, so we'll center drill it 30 thousandths deep. All right, and then what we're going to do is we're going to load up our 1/4 inch end mill, and then we'll just touch it off on the front, and then move in 20 thousandths. It doesn't have to be 20 thousandths, as long as it's something. The dimensions say 20 thousandths, but if it's slightly less, it doesn't much matter. As long as it just relieves this material, and then all of this center section will look like this. So again, so when the piston is going around, it's not going to rub on all this material. It just helps your air engine to run faster and more efficiently, right? Because you're taking out all this potential friction. All right. So that's basically what back facing is. Excuse me. We'll go out in the shop and I'll demonstrate putting this crank together and then truing it up. All right, we're out here in the shop now. Right here is our Arbor Press. It's going to help us press number 8 and number 11 together so we can assemble our crank. This right here is the Arbor Press. It sits on this workbench. It's bolted down to this workbench that's in the middle of the shop. All right. So right here we've got the ram that goes up and down and applies the force needed. All right. We have a little hand wheel here which helps us move the ram up and down. All right. Once we get the ram in place, we can use this lever right here to actually drive. It will drive the ram down and apply the force. This is what will apply the force needed to press fit these two pieces together. All right. So right here we've got 2 jigs. They're always located somewhere right here on this bench, so they're never too far away. What we have here is just a little pocket here and a through hole. All right. The point of these jigs is to press these two together as perpendicular as possible. It won't be perfect, that's why we're going to put this on the lathe and true it up, but it will help us. If we were just to lay this down like this, we could not achieve, it would be very difficult to get this perpendicular to each other. All right, so we use this little jig to help us out. And to use this jig, we have to look at our crank face. All right, I like to take the ugly side, which is usually the side that you parted off. It should be pretty evident sometimes which side is which. I'm going to say that this is the ugly side. All right, I want the ugly side sticking out of or facing me from the jig. All right, and then what we'll do is I'll keep my finger on that and I'll put this pin through here. All right, so right there it's lining up the crank face with the crank pin. So now they're pretty controlled and captured in there. So what I'll do is this platter right here, you need to find a spot where as this is pushing you, we obviously don't want to push down in the hole, right? So we just spin this platter around so it gives us a nice flat surface to press. All right, and what I'm going to want to do is put this jig down like this. I'm going to be pressing the pin and not the crank face. All right, so I'll place it down on there, and with the little hand wheel I'll just bring this ram down and I just want to put this somewhere in the center of the arbor, of the ram here. If I come out over here, it's going to press it at a weird angle. All right, so I just kind of center it up in the center of that ram. Now I'll just use the hand wheel just to bring it down and make contact. All right, so once we got it set up there, now we can start applying some pressure. But here's the caveat. All right, so this puts an incredible amount of pressure on this. All right, we can really crank down on this, and if you do, you end up bending your pin and you have to start all over. You got to make a new crank and a new crank face. All right, the pin and the face. So that's 2 parts if you don't do this right. So there's some little tricks that I like to do. All right, first, do not crank down. Don't pull down on this like it's a parachute cord, okay? Just very light pressure. You should feel that pin starting to slide into the hole, all right? So I'm just gonna press it in just a little bit just to get it started, all right? There's just a little bit of pressure, all right? I could feel it just barely starting to slide in there. Now, what I like to do is I can take it out and we can see that it's starting to get together, all right? It's just barely hanging on, but it's there. And what I like to do, I'm not sure if it's gonna be easy to see on the camera, but I like to go and I like to rotate it with my hands to see how true it's running, all right? Sometimes people get these in really crooked from the get-go, all right? I'll try to make it look crooked. All right, that's actually going in pretty straight. So, but you'll notice if you roll it in your hands and the crank starts doing like this, what I like to do is we took it out like this. I like to put it back on kind of backwards, all right, like so. And what I'll do from there is I got it, this pin sticks out of the jig a little bit, so I have to move over to a place where the pin can sit, all right? So if your face and your pin are really at a bad angle, don't keep pressing it in because it's gonna keep going in that bad angle. What I can do now, since it's just barely holding on, I can come back like this and apply pressure, all right? Kind of pressing it back together. And what that's gonna do is hopefully if your thing was like this, it will mash the face back down closer to perpendicular, all right? Mine wasn't really that bad, but yours may be a little bit off. So what I do, now that I've re-trued that face up, I'll put it back down and I'll go and I'll press it once again all the way down to the bottom. All right, again, I'm just giving it a little pressure, and just, you can just feel it slide in, and then once you should be able to feel it stop. Once you feel it stop, let go, okay? If I put my full body weight on this, it's gonna bend that pin into a banana shape, and that pin will never run true, and then you'll have to make both parts again, all right? So now that I've got that pressed down to the bottom, you'll know it's down to the bottom because the edge of my pin should be pretty flush with the face of that crank. And then right there's your assembled crank face. We still need to true it up, and we'll get to that here in just a moment. All right, we're continuing lab 6. We're here at the machine shop at the lathe. And the first part we're gonna do today is the spring cup retainer. All right, that's part number 3. All right, it's just gonna be a little tiny part. So when we do have little tiny parts, we can't hold on to little tiny parts in a chuck. So we're gonna have to use it on and part it off a larger chunk, all right? So these parts can be found over by the Arbor Press in the on the workbench in the center of the shop. All right, so this one has parts taken off of it before, so it's going to have this little tapered end and a little hole. All right, so first thing I'm going to do is load it in to the chuck. All right, being mindful that we're not sticking it out too far. All right, something like that will be great. All right, so the first thing, which is always the first thing, is we're going to face off the part. We have to get off this little remnants of the last spring cup being taken off of this, and we need to get rid of that little hole in the center. All right, so we'll just face it down until we have a nice flat front on this. All right, so we'll do our calculations, and I'm going to change the speed. All right, there we go. So let's face this off. I got off that little tapered section, but I still have the little dent in the front, so we'll just move it in a little bit. All right, that was enough to clean up the whole face, and now I don't have the leftover stuff from the last part made on this. Okay, so that was our 3/8 stock that we just cleaned up. And so the next thing we're going to need to do is going to put the through hole in there. The through hole, if you look at the call out, has a diameter of 0.20 through. All right, so we will use a number 7 drill. If mine is stamped with number 7 right down here, you won't be able to see it, but it has a diameter of 201 thousandths. All right, so it's just slightly under, but that's such a loose tolerance that even a drill will be able to achieve that. All right, we're also when we're going to drill this, we need to figure out how deep we got to drill. All right, so we don't want to drill all the way through this piece of material and make it into essentially a tube, right? We just need to drill just enough to make this part. So how do we figure out how deep we need to go? Well, our part is 130 thousandths. All right, so we need to go 130 thousandths. We also know we're going to have to cut this off with our parting tool. And our parting tool width, we need to add to that. That way, when we part off, we can part off into a hole that's already in the center, made by our drill. So this is right at 100 thousandths. Okay, so we'll add that to the 130. So we're at 230 thousandths. We've also want to account for our drill tip, which is roughly 1/3 of the diameter. So this is 200, so we'll round it up to 210 and we'll divide that by 3, so it's another 70 thousandths. So just approximate, another 70 thousandths. So if we add the width of the part, which is 130, the width of our part off tool is another 100, and this 70, we should come up to 300 thousandths or thereabout. Okay, so that's the depth I'm going to want to drill this. So before we start drilling, we always need to center drill. So let me get this tool post out of the way. We'll bring our tailstock down here. And we'll put in our center drill. Alright. And then we'll just put that little spot in the center. Alright, just get it up close and we'll lock it into place so our tailstock doesn't slide. Alright, now we got to take this tool out. All I did is just put a little spot right there and enough for the drill to follow. Alright, so now I'll put in our number 7 drill. Alright. So since one full revolution of this handle is 100 thousandths, I'll just kind of take note of where the handle is when I start making contact, and I'll do 3 full revolutions from there. Or you can just get it up. One thing I like to do is that the handle is down at the bottommost part of the wheel here. And I'll just slide it up just barely enough to make contact. I'll lock it into place and then just pull it off just a little bit, because I don't want to start up the lathe with the tool already engaged. So I've just backed off enough of it. So I know when I come down to the bottom I'll be touching it, and then I'll do 3 full revolutions of this handle. Alright, so let's put a little cutting oil on here. Alright. So there we go, 3 full revolutions. 1, 2, 3. Now just come on out. All right, that's looking really good so far. These chips out of here. Before we go anywhere else, we're going to take this drill out. All right. So that will be our 200 thousandths through hole. All right. Now, if we look at that feature, it also has the counterbore. We discussed what that counterbore symbol and how to achieve that. All right. The counterbore has a diameter of 0.31. 0.31 is very, very close to 5/16. All right. So what we can do is we can load up a 5/16 end mill and then plunge in 60 thousandths and then make that counterbore the way we need to. All right. Here's our 5/16 end mill right here. All right. This is a 2-fluter, meaning that it's only got 2 cutting edges, one right here and one right here. All right. And that measures 5/16 in diameter, which is 0.3125. All right. So this will be able to make the counterbore the right size that we need it. All right. So there's a couple things as I load this that we need to talk about. First of all, you've probably been told already that we never put end mills in a drill chuck. And this is a drill chuck, remember? Drill chuck has the 3 fingers that come in and we tighten, and it's used primarily for drills. All right? We should never put end mills in a drill chuck. The one and only exception is when we're using this end mill like it's a drill. All right? When we go into this material, it's just putting force straight axial, in an axial direction, straight up here. All right? If we did this on the mill and we started moving this around in material and we started putting radial forces, it will break your tool, it will break the drill chuck, and it will ruin a lot of things. It's a very dangerous event when you do that. So the one and only exception to have an end mill in a drill chuck is when we're using it like a drill. And essentially we're turning this into a flat bottom drill. All right? So all we're gonna do is just straight plunge into this, which all the forces are axial. Once we start getting radial forces, that's when disaster strikes, okay? So, if you've heard no end mills in the drill chucks, this is the one and only exception to that rule. All right? The second thing I'd like to talk about is I consciously, every time we use a drill or center drill or reamer or whatever we're using in this drill chuck on the lathe, as soon as we're done using it, I take it out, all right? And what that does is help build a pattern, a habit of taking things out. Because right now, as this sits, this is a very dangerous setup, all right? What can happen is if you start leaving end mills in a chuck like this becomes like a scalpel, all right? These are as sharp as a scalpel in a helical fashion, all right? So I've seen people where they have left these in here and then start digging around in the machine looking for their part or trying to clear chips with this scalpel just hanging out in the air, all right? And if you reach over there and it starts ripping up these part of your arms, you're gonna have quite a cut, all right? Very, very dangerous setup right here. So when I use this end mill, or any tool in fact, all right? Even a drill can cut you if it grabs you the right way, all right? It's very important to take the tool out. All right, so that's my little safety spiel for a second, all right? So we've got the appropriate sized end mill loaded up. It's a 5/16, all right? And now we have to go plunge into this material to a depth of 60 thousandths, all right? One way I like to set this up is, again, I'll just kind of get this out a little bit. And I like to start with the handle of the wheel down at the bottom. It's just a personal preference. And I'll just make sure that that reads 0 here on the handle. Can we see that? All right. So I've just zeroed it out on the handle down here. My handle is at the bottom of rotation. And what I'll do is just lightly tap it. Just lightly tap it till it makes contact. All right? Just barely makes contact with the front. So now the front of my tool, of my end mill, is touching my part. And I'll go ahead and lock down my tailstock. And now I know 0 is right at the front of this part. And all I'll do is just come off a little bit. That way when I start this up, my tool's not engaged, all right? So I'll turn this on. And what I'll do is once I turn it on, is I'll move into 60 thousandths, all right? You probably won't be able to see me turning the dial to 60 thousandths, but just watch the tool as it plunges in, the end mill. All right, I'm right at the front of the part, and I'll just use some cutting oil and go in 60 thousandths. There's 40, 50, 60, and I'll come straight out. All right, let it wind down. You may have chips and stuff on your end mill. I advise you to not grab it with your hands, but take it off with a towel, right? You'll save your fingers. All right, move this out of the way and immediately take it out of the drill chuck. That way I don't forget it's in there. All right, so I've taken that out. All right, our part's looking really, really good so far. All right. So now we've got that counterbore in there. Now the last step that we have to do is just part this tool, or part this part off. All right, just part it off to the correct size, and that will be that part. It'll be all done. All right. So I'm going to put my tool in here. I've already got the height set on this. All right. But what I need to do anytime I use this tool is I can't shove it in sideways like this. It has to be perfectly parallel. All right. So there's a couple different techniques of doing it. This is just the way I like to do it. I loosen up the tool post, and so it can slide around. And I'll just bring it up to the part, like so, and I can touch off any part of this tool along here. All right. What I'll do is just bring it in and let it rotate the part right where it needs to be. And I'm looking down, making sure it's good and perpendicular to the center of rotation, which that looks pretty good. Move it around by hand and really get it on there. All right. Sorry if my head's in the way. All right. Once I've got that set up, I just move it off and tighten it up. There, I've tightened it up. All right, so we got our tool orientation. That's probably the most important part of parting something off. It's getting it to plunge straight into the material. If you bring it in sideways like that, you'll break this whole, the whole tool and tool holder and everything. Okay, so we have to part this off to a width of 130 thousandths, plus or minus 10. That's a pretty big tolerance, okay? So instead of getting too exact with dialing everything in, there's a little quick shortcut that I like to use, all right? And all I need is my 6-inch scale, all right? And what I'll do is put it on the front of this part, all right? That way I can rub it across here like so, all right? And with the carriage, I'll just bring the tool down. It may be difficult for you to see, but I'll just bring the tool down with the carriage. And I just kind of keep going across the front of this part. All right, slowly bringing the tool down. All right, until the front of that part and the 6-inch scale. So about right there, the front of this part and the right side of this tool are essentially right in order, or right in line, all right? Certainly well within the 10th thou tolerance, all right? So that's just a quick little way of setting up a tool, all right? So now I know the right side of this tool is along this front face and they're in line, all right? Now we can go to our compound dial and set that to 0. All right? So now that I've set that to 0, now I can just go in the amount I need to cut this part off, which in our case is 130 thousandths. All right? So there's 130 thousandths. All right? So that's our thing. That's right where we need to be. All right? And we also need to slow this speed down just a little bit. All right? Because we need slow rotations or slow speed. All right? Because we're plunging right through the side of this part. All right? All right, I've slowed it down. And now we'll go to cutting it off, parting it off. All right? Here's a little cutting oil. I'm just going to go plunge in. But one thing I will say is before we cut it all the way through, while it's still connected to the material, it's a great opportunity to deburr both sides of this part. Alright, so I'll stop short of cutting all the way through this. That way I can file both sides. I just went in just a little bit there, all right? And then now I can use my file and I can deburr this side right here and this side, both sides of my part, okay? I just laid my file in that, just work it a little bit, and on the front of the part as well, just a little bit. I can also take my center or my chamfer mill and then chamfer the inside hole right there just a little bit. You won't be able to get to the edge of the counterbore, but if you just offset this a little bit, you can usually grab just a little bit of the inside of that counterbore. Just enough to break it. So, got that all cleaned up. And then now I'll just finish parting it off. Alright, we should have a nice ribbon-like chip. Alright, there it goes. Popped right off. Alright, one thing about this. Alright, so that's it for that. Take this tool out of the way. That part coming off when you part things is extremely hot, all right? So don't get in a big hurry to go find it and grab it. It probably is a little hotter than your hands want to touch, all right? So our ribbon-like chips look like that. That's what your chip should look like when you're parting off. If they're just small little crumbles and it's like this, some sort of things, you're going too slow and all you're doing is building up heat. So you want to feed it enough to have a nice little ribbon. It should start coiling up and everything and looking nice. Alright, so here's my piece. Alright, it's just a little tiny thing. Alright, I do have a little bit of burr left over from parting it off. Usually if I just flex it, it will just pop right off. And I can also take my little chamfer mill and just cut that burr down so it's not sharp. Alright, so that feels pretty good. So let me blow it off. There we go. So that's our little part. Alright, it's just a little tiny part. And that's what it should look like. So this is our counterboard side. That's got a 5/16 diameter and it's 60 thousandths. And that's the back side. We can go through and measure this. It's not a high precision part. But look at right there. 130 thousandths right on the dot. Alright. So I kind of got a little lucky right there. But the tolerance on this is pretty wide open. So that's how your part should look. Alright, so that's one of the parts that's due for lab 6. There it is. Alright, continuing with lab number 6. Right now we've got our crankshaft assembled. We did that over at the Arbor Press. Now it's time to balance this out. Alright, so we'll use the lathe for that. So the first step we want to do in order to balance this out, I said, was to use the Sharpie. Alright, I want to have a Sharpie that covers all of this surface. Alright, I want to Sharpie the outside diameter. Like so. Now I also want to Sharpie this back face. as best as I can. All right. There we go. I colored it all in. If I get some on the actual shaft, it's no big deal. It will wipe away. All right, there we go. Looks like I passed first grade pretty easily. Right there, I colored that in. Stayed in the lines. All right, so now we've got a black surface on the 3 surfaces, 1, 2, 3, that we're going to want to machine on. All right, so what I'm going to want to do is now load this into the chuck. And I don't want to chuck it up so much that I can't get to this backside. Remember, we're going to have to back face this, so we've got to leave this sticking out enough where we can get a tool in here. All right, and one way I like to do that like to clip, just snug it down a little bit. And since we know we're going to have to measure this, I like to have enough room in here where I can get my calipers on this. All right. If this thing is shoved in so far and I can't even get my calipers on there to make a reading, we're not going to be able to really balance this out and get it to the size. So that means I like to have enough out where I can get those calipers on there. All right. We don't have to hold on to a whole lot. All right, because remember with this we're taking light cuts. So we're not going to be generating a whole lot of cutting force. But right there I'm able to get my calipers to make a reading on this. All right, I'm going to snug it down. I'm not going to crush it, because if I crush it too much, when I'm just holding a little bit, I'm going to make 3 flats on the shaft and get it all out of sorts, and it's not going to be able to slip through the parts that it needs to. So I've clamped onto it firmly but not crushed it. I've got it out long enough where I can do all the machining just on the crankcase. Okay, so the first thing we're going to do is take our right-handed tool. All right, my right-handed tool, and get in the position. Now I need to change my speed. All right. Go. And then now what I'm going to do, remember we're just kissing off just enough so all the black goes away. All right, all that Sharpie marker goes away. All right, and we're only talking 3 to 5 thousandths worth of cuts at a time. All right. So what I like to do is move slowly into this. I'll just get it somewhere out in front, and then with my compound, since I have more control, I'll just go really nice and slow until I just barely make contact with that front face. I just barely made contact, and I'm going to come straight out in my X. Alright? So I just barely touched it. Now I want to go in maybe 2 to 3 thousandths. And then make a facing cut. I'll stop the machine, I'll stop the lathe, and just inspect it, all right? So I'll look out here at the front, and it's all cleaned away. I don't see any more black. All right, so I only did a 2 thousandths or 3 thousandths cut, all right, Mine was running pretty true, but the more yours is off, the more you'll have to cut off. If you're taking off more than 7 or 8, it means your thing was really out of balance, and you may have a hard time balancing it all up. That would have been something that you should have addressed back at the Arbor Press. But mine was running pretty true, so with the 2000s cleanup, I was able to clean that whole face off. All right, so now we can assume that this face is now perfectly perpendicular to the center of rotation. All right, now we have to address the outside diameter right here, okay? Because again, when they extrude these, it could be in all different shapes. It's not truly round. It looks round to the naked eye, but it's not actually round. And if we get it round now, it's going to help us later on when we have another operation to do on this. All right, we're going to at some point have to take this over to the mill and put that, if you look at your drawing, that off-axis hole, that's going to have to be done on the mill. So the more round this is, the easier it is to be able to find center. All right, so if you have something egg-shaped or football-shaped, it's going to be very difficult to find the center of that later on. I know you probably don't know what I'm talking about, but just trust me, the more round it is now, the more time it saves later on. So we're just going to clean up this outside diameter. Again, being very gentle. Alright, I just made very little contact. You probably heard it chattering. That just means it's not touching enough material to actually make a cut. Alright, so it was more just rubbing and vibrating. Alright, so now I can go down to my cross slide here. And then I'm going to just try 2/1000ths, all right? So that's just 1 tick mark, all right? Move in 1 tick mark. All right, so I moved in 1 tick mark, and this actually works out well because you can see how I've gotten down to the metal here and taken the Sharpie away, but I turn it around and now I still have Sharpie over here. So that can show you that right here was a high spot on that metal when it was extruded, and I just barely got up underneath that high spot, but all back here, the tool hasn't touched yet, all right? So that's what you're kind of looking for. So what I'm looking for is for it all to be the steel color, all right? So what I'll do is I'll move in just 1 more tick mark. So I took another 2/1000ths off, and you can already see that there's still some black here, and there's some silver, so I'm about halfway there. All right. So I'm going to just keep on going until it's cleaned up all the way around. So it does look like I've still got a little bit black right there, so I'm going to do 1 more pass just to make sure it's good and round. So I can tell now that it's good and cleaned up all the way through. All right. So it looked like we took a whole lot off, but we really didn't. So we're only talking little tiny amounts like this off that surface. All we did is just made that irregularly round thing truly round. All right. So our last surface is the back face, and this is where we get our back facing. So I'm going to take off my right-handed tool that we have ground, and now we're going to use the left-handed tool. Actually, let's look at them side by side. All right. This is the part you'll have made. All right. That's your right-handed tool. Right here is our left-handed tool. All right. The only difference, here I'll put my hand here so you can see. The only difference is that it's a mirror image of each other. This one is ground on a smaller stalk than this. All right. That's just so we can get back in there behind the back face there. But the geometry between this and this are the same. All right. They're just mirrored. All right. So we'll take our left hand tool. We do have it kicked in the tool holder to an angle, to a pretty steep angle, but that's again just so we can be able to access down in here. All right. We don't have a whole lot of room, so sometimes you have to kick this at an angle so you can get into there. But the principles still remain the same when we're adjusting the orientation of our tool. All right. So when we use our right hand tool, we're trying to get everything down here in the fourth quadrant, right? If we're looking at it from the top down, you want the tool to be somewhere in this quadrant. The only difference that we're doing now is now we need this tool to fit in the third quadrant. All right. So that's the only difference. That's your right hand. It needs to stay in that quadrant. Your left hand tool has to stay in this quadrant. All right. So when I adjust this, I kind of park it where it needs to be, and then just take a look to make sure my orientation's right. Which that looks good. This one's been ground to a sharper point. That gives me a little bit more access back there. All right. And before I turn on the machine, one thing that's key is to get it. I like to park it very, very close to where it's going to end up, and then rotate the chuck by hand. I do that so I know that when I cut this chuck on, it's not going to crash into this tool. All right, because we're dealing with a pretty small space here. So what I don't want to do is turn this on and then just have the chuck jaws smash into my tool holder. All right, so that's about where the tool's going to end up. All right, more or less. So we can see that nothing's going to hit. All right, so I'll just pull it straight out and start it up. One thing I forgot to mention is, unlike what we've been doing before, where we had to go in this direction with our cross slide, or excuse me, our compound, to drive it this way, we're going to actually have to be pulling it this way to make a cut. All right, so don't go in here because you'll drive your tool. Don't go the same way you've always been doing when you're doing facing like this. We have to go in this direction. If you go this way, obviously you're going to send your tool into the chuck. All right, that's a bad day for everyone. All right. Very, very, very light cuts. All right. Now I'm going to go in this direction in the positive Z just to make contact. I just made contact You may have heard it chirp a little bit. All right. So I'm just going to do a 2 thou pass each time. All right. So I'm going to go in this direction 2 thousandths. 1, 2, and then make the cut. And I'm going to make that cut all the way until it hits the shaft. All right. There should be a noticeable change in sound when you hit that. It'll probably start chirping a little bit. You may hear it chirp when it hits that pin, but you should be able to feel it, okay? You can't see this on camera, but there is a little, probably a half moon shape that I still haven't cleaned up yet, all right? So I think probably another 2 thou pass should be able to clean this up. Let's see. So I'm going 2 thou in this direction in the positive Z. All right. I'll just inspect this back side. And it looks cleaned up. It looks very good. All right. So from there, we'll take out our left-handed tool. All right. So now our crank face is nice and balanced. All right. Any cuts we make on this everything will be in balance from here on out. All of our faces are perpendicular or parallel to their respective faces, all right? However you want to look at that. All right, so we're balanced. So now what we've got to do is take our right-handed tool and put this back in. All right, we'll put it back in, lock her down, and now we're going to end up facing this to the correct width, which on your drawing says 123 plus nothing minus 2 thousandths. So I'm going to shoot for 122 thousandths. All right. All right. So I've actually preset my compound slide to 0, and then what I'm going to do is just kind of cheat up on this face and make a cut. All right, it should be about the same as just rubbing the tool on the face. All right, from there, all I did was just barely touch it and then ran the tool across that face. I've already preset my 0, so the face of this is already zeroed out. All right, so let me go straight out in the X and measure this. All right. So I'm at 142 right now, 142 thousandths. I need to go down to 122. So that means I got 20 thousandths to go off, to take off. All right. So it's going to be a handful of passes because I only want to take 3 or 4 thousandths at a time. So I'll probably try 4 thousandths passes. So 5 4 thou passes. right, so I'm going to go 4 thousandths in a negative Z. There's 4. There's 8. There's 12. $16. And there's 20 thousandths taken off the face of this, all right? Before I take and move everything, we're gonna verify that what I did cut and what I expected to cut are the same, all right? So I wipe these faces off, and we should have 122. Which for some reason we don't. We're still at 130. All right, so 130, that means I still have 8 more thousandths to go. So I'll do a couple more 4 thousandths pass. That's why I always measure before I take things out, or take tools out of the machine, or take my part out of the machine. I always want to cut and verify. All right? All right, so we're right where we need to be now. So we can take this out. All right. So so far we've gotten the crank face down to the right size, within tolerance. All right. Now all we need to do is put in that little spot face on the front end of this. Okay. And again, that little spot face, all that's going to do for us is to relieve a little bit of that material away. That way, when our piston is working up and down, it doesn't drag across the face of this crank. All right. All right. So to put in that counterbore, that little spot face, if you will, we're going to just go ahead and we're going to center drill it. All right. Talked about center drilling it because we want that material away from the center of the cutting from the end mill. All right. Again, I like to put just my personal preference. I like the handle at the bottom of the rotation. And I'll just bring that up and tap it until it's there. I'll re-zero everything and lock this down. All right. I'll just move off the part a little bit. And now I want to go in 30 thousandths. All right, 30 thousandths with this center drill. It's 10, 20, 30 thousandths. So there's 30 thousandths. It's not going to be much. It'll just be a little dent in there. All right, so we'll take out this. And then that counterbore size, or the spot face size, has been dimensioned out to 1/4 inch. All right, so right now I've got my 1/4 inch end mill. All right, so this one right here is 4 flutes. All right here along these flutes, this diameter right here is 1/4 inch. Along the shank of this is 3/8. All right, so when we get tools, there may be a bunch of different fractions on this. All right, this one, for example, it says 1/4 by 3/8 by 5/8 by 2 7/16. And you're like, well, what does that mean? All right. Well, the only number we really care about for this class is going to be this first fraction, which is your 1/4. All right. That's going to be the diameter of the cutting end. So this down here will be the 1/4. The 3/8 tells you the diameter of the shank, or the part that you hold. All right, so this is 1/4 inch, 3/8. All right, the next fraction is 5/8. All that tells you is how long the flute length is. All right, from this tip to the top of the flutes is 5/8 of an inch. All right, and this next number, 2 7/16, is just the overall length of this tool. All right, so when you look at this, there's going to be a bunch of different fractions, all right, and it just tells you how this tool is shaped and how long it is and whatnot. But for the point of this class, just that first fraction is what we care about, because that's the cutting diameter. So that's going to be this 1/4 inch. All right, so let me load in this 1/4 inch. Again, be very, very careful with these end mills in the tool, or in the drill chucks. Right? We don't need to go home all bloody. All right. So all I'll do again is just tap this so slightly until it makes contact. Tighten her up. All right, and then just come off the part just a little bit so we can start it out. All right, and for this spot face, all we're doing is going in 20 thousandths, so it's not a whole lot of material. All right. So there's 0. All right, 20 thousandths. It's just a little bit. All right. And again, clean this end mill off with a rag and immediately take it out. There we go. Take it out of the drill chuck and get it out of the way. All right. Let me just visually inspect this part. I do have a little spot face there. Everything looks right. All right, so the last thing we have to do is just deburr this. All right, so what I'm going to do to deburr this is going to get this back side, this front side, and then on the face, that end mill can leave a little bit of burr around that spot face. And what I'll do for that is I'll just use this emery cloth on the face just to kind of smooth it out. Right, on the back side, again, just very light. We don't want to pop these apart. All right, that was the two edges, and then now for the face. I just hold that on there real quick, just so it gets nice and smooth, all right? And burr free. All right, let's take a look at it before we take anything off. Everything, all the features are there. The one only feature that's missing on that crank face is the hole that's off axis or off the center of rotation, which will be our pin for our piston. But we can't put that on the lathe, all right? We can't drill off center, all right? So that's a process that we'll have to do on the mills later on in the semester. But everything there looks good, so let's take it out. Let's take it out. All right, so that should be our part. If you zoom in real tight, you might be able to see just a little slight spot face there. You'll probably see the center, where the center drill came in, and you may have that little mark, and that's going to be okay if it's there. It's actually going to help us later on when we try to find the center of this part on the mill later in the semester. All right, so having that little dot there, though it doesn't say it on the print, it's one of those things in manufacturing that helps out the manufacturing end. And it won't keep the part from doing what it's intended to do, all right? So right there, obviously you've seen the outside diameter in this back face. See, it's been free and clear of all that black. So there's still a little bit on the shaft, but that's all right. We weren't cleaning up the shaft. We can take a little alcohol and get that marker off if it bothers us. But there you go. So this crank was nice and balanced and to size. So assembling this and truing it up and getting it to size is also due for Lab 6. So the two things you'd have to do is this and that spring retainer cut, all right, that you just watched. And that concludes lab number 6.